Hello and welcome to our next lesson of exponential functions. Today we are looking at properties of exponential functions, and our learning goal is to be able to determine properties including domain and range, the intercepts, increasing and decreasing intervals, and asymptotes for exponential functions using their table of values, graphs, and just verbally being able to communicate this. And remember, communication marks are part of your course mark, so it is important that you know how to use the correct terminology to be able to describe characteristics of different functions and their graphs. So before we jump into our main lesson, we're going to do a bit of a review from what we've seen so far. So starting with the function y equals 6 to the power of x. So this is clearly an exponential function because our variable is an exponent. And we're asked what kind of function this is. And specifically, we are answering whether this is an exponential growth or an exponential decay. So whether this is increasing or decreasing. So we know that as x goes towards infinity, then 6 to the power of x is also going towards infinity, which means it's growing. So this is an exponential growth. You can also say this is an increasing function, and that's what makes it an exponential growth. Now, similarly, for the next one, we're also asked what kind of exponential function is this function, but now we have y equals 0.8 to the power of x. Keep in mind, this is just y equals 4 over 5 to the power of x. So as x goes towards infinity, so as x is growing, and we are multiplying a decimal by a decimal, we're actually getting our output is getting smaller and smaller. So 0.8 to the power of x is actually going towards 0. So it's not actually reaching 0, but it is getting closer and closer to that value. So this is a decreasing function, and it is an exponential decay. Now, our next question, and this isn't just specific to exponential functions, but what characteristics identify a function? Specifically, consider when you're looking at the graph of a function, what are some important things that we want to know from a function? So, of course, we want the domain and range. We want the x-intercept and the y-intercept. Similar to that, or similar to above, we want increasing and decreasing, or slash. And you will see, or you might have seen already, some functions can be increasing on certain intervals and decreasing on other intervals. So that's why specifically in our learning goal, we did have the intervals there because sometimes the whole function is not an increasing function. It may be increasing from x is greater than 0 and decreasing when x is less than 0. So that's why it's important to have the intervals there. And so maybe I'll add that intervals. Um, Recalling back to our quadratic functions, we also had max and min points, so the maximum or minimum points. And of course, we have asymptotes, which we already saw could be horizontal, vertical, or oblique. And any other ones that you can think of, you can also add there. Those are the main ones, especially when we are looking at exponential functions, the ones that we are mostly working with. But again, there's other ones that you can name there as well. And you can just add it on for yourself. Now, our next warm-up question, So remember with the zero exponent, there is a property to it. It is one of our exponent rules, and we're asked to evaluate the following. So if you remember, 2 to, or any base to the power of 0 is equal to 1, which is our property. So that means I don't even need to look at the base for any of these. These will all be 1. So 2 to the power of 0, or a rational number to the power of 0, an irrational number to the power of 0, all of these will be equal to 1. And one thing I will note, oh, this should have been D, that n just cannot be equal to 0 itself. So it has to be just a non-zero base there. And so again, all of these will just be equal to 1. And finally, how is the graph of an exponential growth different from the exponential, or sorry, the graph of the exponential decay function? So remember with the exponential growth, we have something like this, whereas with the exponential decay, we have something like this. So you can, there's several things you can mention here. You can say growth for the exponential growth, and then for the decay. Now, keep in mind, this, we're not, we haven't introduced our transformations yet, but with the transformations in mind, we don't necessarily always have that they have the same intercept or the same asymptote. So we're just speaking generally for growth and decay. We will just say that this is an increasing function, and this one is a decreasing function. And so what that just means is as x goes towards infinity, y will go towards infinity as well. And in this case, as x is growing towards infinity, possibly y is going towards 0. But again, if we have, for example, consider just the graph of y equals 2 to the power of x. If you do translate this up or down, then your asymptote is actually changing. So it won't be 0, but we will have y is, perhaps, maybe I'll just write it, y is decreasing. Just to make it general. Now, here we are looking at one of our basic exponential functions. So y is equal to 2 to the power of x. So we start by filling in the table of values. And as always, I know this one for sure is just 1. So I start with that. And you can always work your way by dividing and multiplying. So in this direction we are dividing, in this direction we are multiplying, specifically because it's 2 to the power of x. And you can always check this is 2, 4, 8, because 2 to the power of 3 will be 8. And in the opposite direction, because you have negative exponents, we are taking the reciprocal, so 1 to the power of 2, or sorry, 1 over 2 and 1 over 4. So now graphing these points, we do have 0, 1. 1 will be 2. 2 is 4. 3 is 8. And I'll add 4 there as well. And then in this direction, negative 1 is half, negative 2 is a quarter. And if I connect these points, there we go. And then we just do label this as y equals 2 to the power of x. So now, analyzing this graph, we're going to answer the following questions about it. So first, can x be any number? So this is telling us our domain. Can I have any exponent value when I have a base of 2? And yes, we can. X can be any positive or negative real number. Now, can y be any number? And for example, even consider, can it be equal to 0? So can we have y equals 2 to the power of x be equal to 0? Which we saw that no, this is not possible. And in fact, y is actually greater than 0 in this case because of that asymptote or that lower limit. Now, where does the graph cross the y-axis? And that's pretty much our y-intercept. So y-intercept is at 0, 1. So when x is equal to 0, then our function crosses the y-axis. Now, where does the graph cross the x-axis? And we can clearly see that this will, as we go towards negative infinity, we are getting closer and closer to the x-axis, but we don't actually reach it. So we will say the graph never crosses the x-axis. Is the graph increasing or decreasing? We can clearly see that as x is growing, y is also growing. So this is an increasing function. And we say as x goes towards infinity, y goes towards infinity. So what happens as x becomes very large? We just said y, which is equal to 2 to the power x, becomes very large because it's growing. And what happens as x becomes very negative? So here, y is equal to 2 to the power x, approaches but never reaches y equals 0. So this is now, and we did see this last time as well, but just putting all that information together, x being any number gives us the domain that x is in the set of real numbers, and it can be any value. Now, y being greater than 0 gives our range. So y is the set of all, in the set of real numbers, but with the limitation that y has to be greater than 0. We don't have any x-intercepts because the graph never crosses the x-axis, but we do have a y-intercept at 0, 1, which is when the graph crosses the y-axis. And these are characteristics of y is equal to 2 to the power of x. So, oh, and I could probably add one more here for our asymptote, horizontal asymptote at y is equal to 0. Now, first we're going to look at this page here where you have a kind of like a cheat sheet for yourself of characteristics of the graph of a function. And again, this is just all functions. It is not limited to exponential functions, but we are going to review this first and then make connections to some of the functions that we do know. So domain we already have seen is the set of all possible values for x or our input for any function. And the function has to be defined on those intervals. So if there is no actual output for y based on an x value, then that x value is not in our domain. Such as when we have 1 over x, we clearly have that x cannot be equal to 0 because then the function will not be defined. The range is now our dependent value. It is the output, and it is actually dependent on the domain. So the set of all possible values of a produced by the function, but again, it is dependent on the domain. Then we have our x and y-intercept. So x-intercept is where the graph crosses the x-axis, and at that point we do have y is equal to 0. So typically by setting y equal to 0, you will be able to solve for the x that provides the x-intercept. And likewise for the y-intercept, it is where the graph crosses the y-axis, and you will find what that y value is by setting x is equal to 0. Then we have our increasing and decreasing intervals. So intervals where the function increases as x increases are increasing intervals. And as x increases, but the output or the function is decreasing, those are decreasing intervals. So one example I'll give you. Consider y equals x squared, right? When x is greater than 0, as x is growing, then we do actually have that our output is also growing. However, on this side, consider we are working from here and going towards 0, so x is increasing this way, but our output is actually decreasing. So our quadratic function, even the parent function itself, has an increasing and decreasing interval. And the way we would write it is for increasing, we would write x is 0 to infinity, And decreasing would be negative infinity to 0, but not including 0. 0 itself is a special point. It is a turning point, which is defined later on, but we do have here we are decreasing and here we are increasing, so two different intervals for the same function. So we can't actually say that the quadratic function is an increasing function or a decreasing function because it has different intervals. Then we have a constant interval where this is intervals where the function remains unchanged as x increases. So consider y is equal to 3. Any x, this is our horizontal line, right? This is just a horizontal line where y is equal to 3. So as x is changing, y doesn't change. So this is actually just a constant function, and the constant interval will be just negative infinity to infinity, the whole function itself. But sometimes, for example, with piecewise functions, you will have portions of the function that are horizontal. So those are the instances where you might have intervals, but not the whole function is constant. Then we look at maximum and minimum value. So maximum value is the greatest y value of the function, where minimum is the smallest y value of the function. This can be defined on intervals as well. But for example, our quadratic function, y equals x squared, we know that the point 0, 0 is a minimum, right? Because that's the lowest y value of the function. And alternatively, if I do y equals negative x squared, then 0, 0 will be my max because that will be the maximum output of that function. Here we now have turning point, which I just mentioned, and it's a point where the graph changes from increasing to decreasing or vice versa. So for example, here we have decreasing to increasing, and the point where that change happens is 0, 0, so that will be our turning point. Or alternatively, and I will maybe show you, for y equals negative x squared, then 0, 0 is actually our max here, and it will be the turning point because we are now going from increasing to decreasing interval. So that will be a turning point. And you can have more than one turning point in a function, depending on the function as well. So for example, consider something like this, then I can say that on this specific interval, this is my max. On this specific interval, this is my max. So you can have, or sorry, these are my turning points and my maximum values on those intervals, but these will both be turning points for the function. This will also be a turning point. This will also be a turning point for the function because we are going from increasing to decreasing, and then to increasing, to decreasing, and then to increasing. Next, we have asymptotes. So asymptotes are lines that the graph approaches but never reaches. And remember, these can be horizontal, vertical, or oblique, which are just diagonal. And finally, we have end behaviors. So we want to know that as the on the graph, as x approaches infinity or negative infinity, what is happening to the function. So for example, with our y equals x squared function, as x is growing towards infinity, then so is the function. However, with y equals negative x squared, as x is growing towards infinity, our function is actually going towards negative infinity. So for y equals x squared, I might write that as x approaches infinity, y approaches infinity, and as x approaches negative infinity, y approaches negative. Or sorry, as x approaches negative infinity, we're actually going towards y equals infinity as well. It is our output values are increasing. However, for y equals negative x squared, as x approaches infinity, y goes towards negative infinity. And same, as x goes towards negative infinity, y is also going towards negative infinity because of that negative there. Now, don't confuse this with increasing and decreasing. These mean different things because increasing and decreasing depends on whether x is increasing or decreasing. But here we are just looking at our outputs, so it is a little bit different. So we did this a little bit already as I was going through all of them, but here we are asked to determine all characteristics of the parent function for our quadratics, y is equal to x squared. So, starting with our domain and range. So, of course, the domain we can have all values of x in the set of real numbers, and same with range. However, can I have any y values that are negative? Even just looking at the graph, does my graph ever go towards have an output that is negative? No. So then we do actually have a restriction for our range. But in this case, y can be equal to 0. So we write y is greater than or equal to 0 because clearly we have that 0 point there. Next, we have our x and y-intercept. So in this case, they are actually the same. The x-intercept is 0, 0. So is the y-intercept. So the point where the graph crosses the x-axis and y-axis, it happens at the same point, and it's at this point 0, 0, which will be both our x and y-intercept. Then we have our increasing interval and our decreasing interval. So here we see that as x is growing, then the function is growing, so 0 to infinity. Whereas in this case, as x is growing, so from -6, for example, to -4, we will see that our function will actually be decreasing. So we have negative, infinity, and 0. And just with the notation as well, keep in mind, 0 is our turning point, so it's not included in the set. That's why you have the round bracket. And same with infinity and negative infinity, they are not actual values that can be in our function, so they will also get the round bracket. However, if the value is inside of your set, you will have to use square brackets like 2 to the power of infinity, where 2 will be included in the value, but we won't see that for increasing and decreasing intervals because we will have that turning point. And actually, we can even add our turning point here, which happens at 0, 0. Next, we have a constant interval. So this function does not actually have any interval where the function remains unchanged as x is increasing. And keep in mind, it has to be as x is increasing. You can't just pick one point and say it's constant there because x is not changing on that interval. So there has to be at least more than one x value there. So no constant intervals here. Now we have max and minimum values. So clearly we can see that this is a minimum value for us here. So the minimum is at 0.00, and we actually don't have a maximum here because any point that I pick, there will be another point that's greater or has an output that's greater as I move along the graph. So I can write no max, none, which would be different for the y equals negative x squared function. Turning point we already mentioned, and then we have asymptotes. So as we analyze this function, is there any line, horizontal, vertical, or oblique, that the function is reaching but never actually reaches? And you will see that no, because there's no horizontal line here that our function is approaching. There's no vertical line because this keeps growing and growing, so any line you pick, eventually you are going to cross it. And there's no oblique lines here as well, so no, or like asymptotes, none as well. And finally, we have our end behavior. So again, this is just the shape of the graph. So as x is approaching positive infinity or negative infinity. We're just looking at the function. So as we keep going this way and this way, our function is going towards positive infinity. So this being positive infinity, this is negative infinity, this is also positive infinity, this is negative infinity. And same with as x is approaching negative infinity, then our y is still going towards positive infinity. Again, keep in mind, this is not the same as increasing or decreasing intervals because I'm not interpreting this as x increasing. I'm just looking at as this function is going towards this way, which in this case, x is actually decreasing. So don't confuse those two, but this one will be y is approaching positive infinity, and same with here. This is approaching positive infinity as well. And that makes sense, right? Because in both of the end behaviors, we are going towards the positive infinity, or our output is getting greater and greater. Now we're looking at our exponential functions. So we want to determine the characteristics of both of these functions. So in the orange, we have our 2x, 2 to the power of x. And for my purple one, I have half to the power of x or 0.5 to the power of x. These are the same. Maybe let's do g of x. And this one is h of x. Okay, so again, we want to go through this list, starting with our domain and range. So the domain here, x is all the set of all real numbers. And same with our exponential growth, so y equals 2x. We have x is the set of all real numbers. However, when we get to range, we do have a restriction now. Y is the set of real numbers, but y is greater than 0. And same with the range here. Oh, y is in the set of real numbers, but y is greater than 0. Next, we have our x and y-intercept. So neither of these functions have an x-intercept, but they will have a y-intercept, which is at 0, 1, and then x-intercept none. And this will be the same here. The y-intercept is 0, 1, and no x-intercept. Then we have our increasing and decreasing intervals. So this is y equals 2 to the power of x is actually an increasing function. So then negative infinity to infinity is where it's increasing. And I don't even need to acknowledge the decreasing at this point because this is my whole domain. So then I won't even have a decreasing interval. And the opposite could be said about the y equals half to the power of x or 0.5 to the power of x. And in this case, our decreasing interval is also the whole function. So negative infinity to infinity. And again, I don't need to acknowledge the increasing interval because the whole domain is decreasing. Then we have our turning point, which we will have no turning point because these are just increasing or decreasing functions. So there will be no point where we change from increasing to decreasing or from decreasing to increasing. And because of that, we also don't have a max or min because in this case where it's increasing, any max that I pick, I'm going to keep increasing from there. And same with any minimum that I pick, I'm still going to go have a point that's going to be of a lower output value than the point that I've chosen. So there will be no max or min. Same with the 0.5 to the power of x function. Any value that I pick as a maximum, I'm going to have an output that is greater. Any point that I pick as a minimum, there will be another point later on that will have an output that is less than the one that I've chosen. So no max or min for either of these. So no max or min. And same with here, no max or minimum. Next, we have our asymptote and end behavior. Okay, so asymptote, we know now for both of these it will be the same. So my asymptote is y equals 0. It is the horizontal line that my function is approaching but never reaching. And same with the other one, asymptote. Now keep in mind with asymptote, um, and we are actually seeing it with both of these. In the case of the purple function, our asymptote is when x is approaching infinity, whereas in the orange function, or our y equals 2 to the power of x, we actually have the asymptote as x is approaching negative infinity. So it doesn't really matter if the asymptote occurs when x is approaching infinity or negative infinity. It is just when the function is approaching it for any interval. So we can see that in both of these graphs, the asymptote is that x-axis, but how the function approaches it is differently. Here, again, we are going towards the positive x, but here we're going towards negative x. And finally, our end behavior. So, end behavior here. As x is approaching infinity, we see that y is also approaching infinity. We're getting our output is getting bigger and bigger. However, as x approaches negative infinity, y is approaching 0. And it doesn't mean that y will reach 0, but it is approaching 0. Now, for the other one, end behavior, as x approaches infinity here, we can see the opposite. Our y is actually here approaching 0. And as x approaches negative infinity is now where our function is growing. So y is approaching infinity in this way. As x goes towards negative infinity, so as x keeps decreasing, our output actually is increasing. So here, which properties stayed the same? Of course, we have our domain and range is the same. Our y-intercept and x-intercepts are the same. Um, neither of them have a max or min, and our asymptote is the same. However, properties that changed would be, and maybe that's the one I'm going to write, is increasing and decreasing intervals, as well as the end behaviors are changing there. But other than that, the rest of it is the same. So what determines when an exponential function is an exponential growth or a decay, and specifically where? So by now, I hope you are know that once an exponential function is a decay, then it's decreasing. So it will be the whole function is a decreasing function, and when it's a growth, then it will be increasing throughout the whole function. So what determines that? And what specifically of these two functions determines whether it was a growth or a decay? And you should get the base. So when b is greater than 0, or sorry, greater than 1, then we have an increasing function, which makes sense because any value of any real number that you pick that's greater than 1 and you are growing this exponentially, then it is growing and it is increasing. However, when b is between 0 and 1, so it is a decimal, then we have a decreasing function because any decimal multiplied by itself repeatedly is going to be smaller and smaller. So that makes our decreasing function. And remember that b cannot be equal to 0 or 1 because that's going to give us just horizontal lines. So these are our two possibilities for the base, which determines when we have an exponential. So in this case, we have growth. And in this case, we have a decay. And so that is it for our properties of exponential functions. So you have been or you this should be actually more of a reviewed all the characteristics of the graph of a function, made connections to a graph we're very familiar with, our quadratic, and now our two main exponential functions. And you have some practice problems here to review all of those characteristics and see how it works for different exponential functions. And as always, don't forget to check Google Classroom for additional tasks posted, and don't hesitate to reach out if you have any questions, and I will see you all in our next class.